operations safety slides. Okay, so here is where you do need to go over and look at them and memorize, right? But it should, I mean, it should be pretty straightforward. Typical hazards in the unit ops lab are hazards that you have in most labs that you will encounter, right? So you should know what they are. You should know what safe practices, what are the safe practices, how can you protect yourself, right? What is proper protective equipment, right? What is it that you have to think of when you select gloves, for example? And then the potential hazards of gas cylinders. Okay, you should know that there are 7 potential hazards with those. And then the NFPA diamond and the pictograms are in there, so that you know they are pretty straightforward, right? But I want you to be able to look at the pictogram and know what the hazards are with that chemical, right? Again, awareness is key. And then what the fire triangle is. That is also in the book. It's in chapter 6. So we're gonna cover a lot more with fires, right, later on. There's a whole chapter or 2 on fires. So all you need to know by now, right, is that you need fuel, and there are different fuels, solids, gases, and liquids. You need an oxidizer. It doesn't have to be oxygen. Chlorine gas, for example, is a powerful oxidant. Nitrates. And then you need an ignition source. But it doesn't take much to ignite a flammable mixture. So, okay. So just in summary, we have course notes. They're included. So, but obviously, so you have all the PowerPoint point slides from the lectures. That will hopefully help you too to see what has been covered. We have worked a lot of problems in class, and that's been part of homework. I have added some suggested problems in the previous exams. So just a reminder, you do need a paper copy, and do not write solutions in the book, okay? All right. That is grounds for an automatic 0 on the exam. Okay, and harsher precautions, and harsher punishments. Yes?
Just to clarify, the Fahrenheit to Celsius conversion is okay to write in the book?
The Fahrenheit to Celsius conversion is okay to write in the book, yes. And just to repeat, I know you've seen this before and you're probably tired of it. You know, you'll have the honor pledge, backpacks, bags, everything goes in the front. I will ask you to remove hats. Do not bring cell phones. I do not want to catch a student with a cell phone on you, okay? That is another automatic ground for a 0, okay? And you cannot have any printed material other than the textbook, right? So printed solutions is not okay. And that goes for, right, solutions in the book written as well. Obviously no talking. And the last one is the one that could be somewhat problematic, okay? Students should not leave the room, may not leave the room before turning in the exam. Okay, I have not stopped a student from going to the bathroom, okay? But I am gonna remind you to go before, all right? And you should also know that if you do leave, your exam will be scrutinized a little bit harder, right? Just to make sure that there isn't, because as soon as you leave the classroom, there's always ground. There you might have had a cell phone on you that I didn't know of, right? You know what happened last year? A student, I did give a student permission to leave, but he had his cell phone on him. Okay, so I don't want to have to do that again. And as soon as the first student has turned in their exam, you cannot leave. Okay, that's the other rule. Okay, that one I have stopped. Okay. So, any questions on that? All right, so we were working on this one. We had started on this one, and we had set up, or we were working on the material management balances. So has anyone solved this already? What's the answer? Did everyone see the note here so I can take it about E-Fair training day? Tonight at 6. I'm sorry, I'm gonna have to erase this. So read 6. Okay, so let's see where we were with this. So this is sort of the backwards problem from what we have done before. This one, we actually have the velocity through the pipe. Do we?
Yeah?
Yeah. We have the volumetric flow rate and we have the diameter of the pipe, so we can calculate the velocity through the pipe. And of course, well, we're gonna set up the mass and energy balance here over this, and we're gonna at first ignore the hole to calculate the pressure. Because once we have a hole there, some liquid will leak out, and that's unknown, which means that the velocity that's going into the tank is unknown until we calculate the leak rate. But it doesn't change the pressure. The pressure up here, right, is determined by the pump at the other end. So we're going to assume that the pump can keep the pressure constant even with a leak here. Okay? So. I'm going to call this volumetric flow rate is 10,000 liters per minute hour. Okay, so that's cubic decimeters per hour. It comes in here. And you know that this section is 3 meters. We have another section here. That's 3 meters. This one is vented, which means that inside here we have Pg is equal to 0 because it's vented to the atmosphere. Okay, so our delta P over rho plus delta mu squared GC plus G over GC delta C plus our F term is equal to 0. Okay, no shaft work. Okay, so this is where we were starting, right? And it's critical to define what your system is in this case, just like in thermo. So we had put a box around here. This is our system. This is our point 1. Okay, and this is our point 2. Which means that it does not matter what happens to the liquid after it goes down in here. Obviously it's going to lose potential energy again, but we still have to overcome that potential energy from here to here. Okay, so delta P, our delta P is equal to what? I know we covered this. It will be P2 minus P1 So if P1 is atmospheric pressure, right? We could also write this. I said, this is, what did I say? I would say P2 is our atmospheric pressure.
I'm just gonna equal minus P1 gauge.
Yeah, so we can write this as minus P1 gauge. Okay, our delta U is equal to U2 minus U1. I think we did this too, right? It is 0 because whatever, right, whatever goes in here is coming out here. That's after the leak now too, right? It will still be the same, but we're gonna ignore the leak for the time being while we're calculating the pressure. Okay, so that's 0. Our delta Z is equal to C2 minus C1, which is equal to
3.
very good. Okay, and it is plus 3, just to make sure. Right? Now you could argue there's probably these elbows add a little length, right? There's actually this length is 1 meters. So, but we're not given what that length is. It might add, you know. So we're gonna assume that this is not to scale. That little length here is negligible compared to the meters. You know, if this was on an exam, I would either, you know, specify what that is, or you could ignore it. Okay, and so the friction factor here is equal to our sum of K friction losses. So what do we have? Entrance term? Say that again?
Saying, considering that, you know, it's a long pipe or whatever, we just assume that we have an exit.
Yeah, so the answer here, right, it's, the hole is inside of a pipe. So the entrance term is way up ahead where we are, right, way before here. So we actually don't have an entrance term. Okay, so this is 0 for entrance.
Skin friction.
And then we have pipe friction, which is our 4FL. So the length of the pipe is 3 meters plus 3 meters plus 1. Okay, 3 plus 3 plus 1 meters. Over our diameter, I'm just going to write this in here. Diameter was given in the problem, and it is 50 millimeters. So it's 0.05 meters. Okay, so this is the pipe term. Okay, what else?
Elbows.
2 elbows. 2 elbows. 1, 2. So we're going to say 2 times, and I'm going to just write K1 over Reynolds number plus K infinity times 1 plus 1 or ID in inches. And then we are going to have 1.0 as the exit term. Okay, so let's look at what else is given in this problem before I take it off. We have the flow rate, we have the inner diameter, the pipe. The pipe is commercial steel, which is important for our pipe, right, for the pipe friction. And then we're given the density and the viscosity. Okay, so we have 2 elbows. That's all it said. If you look at this thing here, you can see this. This here suggests that they're bolted on, they're flanged. Okay, they're not screwed on. And that's the typical one. They're usually flanged or welded. Okay, so our K1 is 800, and K infinity is 0.25. And then we were told that it's commercial steel, but we weren't given whether it was new light rust or general rust. Okay, so we have to decide what to use here, right? We know it goes from 0.046 millimeters to 2. Okay, so I'm gonna take this off so we can continue. Okay, so our elbows will give us K1, what did I say, was 800. So it's 800 over the Reynolds number plus 0.25 over 1 plus 1 over our diameter of the pipe in inches. So 5. So 5 centimeters is roughly 2, okay? 2 inches. I have the exact number. Okay, that's, okay, let's write it out, I wrote it in. It's 1.97. 1.97 inches. Okay, now since we have U, our U is given, right? It's our flow rate over the area. So we have 10,000 cubic decimeters per hour over pi times 0.5. Okay, that's 0.5. I guess I did this calculation in decimeters. Times 2.5. That is 50,929 decimeters per hour, which is 1.415 meters per second. Okay, that means our Reynolds number, which is dV over rho. Just a reminder to mark that equation in your book because it doesn't have an equation number. Okay, we've got 50 times 3 meters times 1.415 meters per second by 928 kilograms per cubic meters per given, and so is the viscosity. Oops, 4 kilograms per meters a second. So that means our Reynolds number is 16,411. Which means what exactly?
Turbulent.
Turbulent? Fully developed? Nope. So we have turbulent flow. But not fully developed. Which means we're stuck with this equation. Right. Which, in this case, is okay in terms of Reynolds number, but the problem is we have an F in there and we have an F in there. Okay? So, one way to do this, of course, is you can go to the graph. Okay? So you can read it up.